All right, welcome to Chapter 11, Chemical Kinetics, Accounting for Rate Laws. Even quite simple rate laws can give rise to complicated behavior. The fact that the heart maintains a steady pulse throughout a lifetime, more or less, but may break into fibrillation during a heart attack is one sign of this complexity. On a less personal scale, reaction intermediates come and go, and all reactions approach an equilibrium. However, the complexity of the behavior of reaction rates means that the study of reaction rates can give deep insight into the way the reaction actually takes place. As remarked in Chapter 10, a rate law is a window to the mechanism, the sequence of elementary molecular events that leads from the reactant to the products of the reaction it summarizes. So, starting with reaction schemes. So far, we've considered very simple rate laws in which reactants are consumed or products are formed. However, all reactions actually proceed towards a state of equilibrium in which the reverse reaction becomes increasingly important. However, many reactions proceed to products through a series of intermediates. In industry, one of the intermediates may be of crucial importance and the ultimate product may represent waste. So, starting this discussion on the approach to equilibrium. All forward reactions are accompanied by their reverse reactions. At the start of a reaction, when little or no product is present, the rate of the reverse reaction is negligible. However, as the concentration of products increases, the rate at which they decompose into reactants becomes greater. At equilibrium, the reverse rate matches the forward rate, and the reactants and products are present in abundance, given by the equilibrium constant for that reaction. We can analyze this behavior by thinking of a very simple reaction in the form which follows, where we have a forward reaction where A is proceeding to B, and the rate of formation of B equals K times the concentration of A. Or the reverse reaction, where B is going the opposite direction towards A. And this can be thought of as the rate of decomposition of B, where you have K prime times the concentration of B. So, a brief comment. Throughout this chapter, we write K sub R for the rate constant of a general forward reaction, K prime R for the rate constant of the corresponding reverse reaction. When there are several steps, A, B, etc., in a mechanism, we write the forward and reverse rate constants of K sub A, K sub B, etc., and then K prime sub A, K prime sub B for the reverse, respectively. So, with that taken care of, for instance, we could think of this scheme as the interconversion of coiled A and uncoiled B DNA molecules. The net rate of formation of B, the difference of its rates of formation and decomposition, is as follows, where you have the net formation of B, the uncoiled state, equals the rate constant of the concentration of A minus the reverse rate constant times the concentration of B. When the reaction is reached, so think of it like this again. You are now looking at the net formation being a combination of the formation of B and the decomposition of B. When the reaction's reached its equilibrium, the concentrations of A and B are concentration A equilibrium and concentration of B equilibrium, and there's no net formation of either substance because you have an equal rate of formation and rate of decomposition. So therefore it follows that K times the concentration of A at equilibrium equals K prime times the concentration of B at equilibrium. And therefore, that the equilibrium constant for the reaction is related to the rate constant by the following, where big K equals the concentration of B at equilibrium over the concentration of A at equilibrium, which equals the rate constant, K, over K prime. If the forward rate constant is much larger than the reverse rate constant, then big K is going to be substantially greater than 1. If the opposite's true, then big K is going to be substantially less than 1. This result is a crucial connection between the kinetics of a reaction and its equilibrium properties. It's also very useful in practice, for we may be able to measure the equilibrium constant and one of the rate constants, and then we can calculate the missing rate constant from equation 11.1. Alternatively, we can use this relation to calculate the equilibrium constant from kinetics measurements. This relation is valid even if the forward and reverse reactions have different orders. In that case, we may need to be careful with units. For instance, if the reaction A plus B proceeds to C is second order forward and first order in reverse, the condition for equilibrium is as follows, where K times the concentration of A at equilibrium times the concentration of B at equilibrium equals K prime times the concentration of C at equilibrium, and the dimensionless equilibrium constant in full dress is as follows. In this case, the presence of C equals 1 mole per cubic decimeter in the last term ensures that the ratio of a second order to first order rate constants with their different units is turned into a dimensionless quantity. So you just have to take a little bit of care when facing that. Now, equation 11.1 also gives us insight into the temperature dependence of equilibrium constants. So, quickly, going back, looking at 11.1, first, we suppose that both the forward and reverse reactions show Arrhenius behavior. As we see from figure 11.1, for an exothermic reaction, the activation energy of the forward reaction is smaller than that of the reverse reaction. Therefore, the forward rate constant increases less sharply with temperature than the reverse does. Consequently, when we increase the temperature of a system at equilibrium, K prime increases more steeply than K. And the ratio of K to K prime is therefore big K decreases. This is exactly the conclusion we drew from the Van Hoff equation, equation 715, which was based on thermodynamic arguments. So, equation 11.1 tells us the ratio of concentrations after a long time has passed and the reaction has reached equilibrium. To find the concentration at an intermediate stage, we need the integrated rate equation. If no product B is present initially, we show in the derivation in the text the following. Where the concentration of A naught is the initial concentration of A. As we can see in figure 11.2, which we'll jump to in just a second, the concentrations start from their initial values and move gradually towards their final equilibrium values as time approaches infinity. We find the latter by setting t equal to infinity in equation 11.2, and using the following assumptions can determine equations 11.3. Which now relates the concentration of product B at equilibrium to the initial concentration of A times K over the sum of K plus K prime. Or alternatively, the concentration of A at equilibrium is equal to K prime times the initial concentration of A divided by the sum of K plus K prime. So before moving on, let's jump back into these figures. Figure 11.1, we can see the reaction profile for an exothermic reaction. The activation energy is going to be greater for the reverse reaction than for the forward reaction because we have a much more substantial barrier to approaching the transition state from the product side than from the reactant side. As a result, the equilibrium constant shifts in favor of the products as the temperature is raised. If we take a look at figure 11.2, we can see that the approach to equilibrium of reaction that is first order in both directions, and here we have taken K equals 2K prime as for the example. Now, note at equilibrium, the ratio of concentrations is 2 to 1, which corresponds to big K equals 2. Now, having wrapped this up, let's move on to relaxation methods. And no, I'm not talking about it being the end of the semester and it's sunny out and we're outside with our grill and our feet are up and we're taking a nap in the sun. Not that kind of relaxation method. The term, in this case, relaxation, denotes the return of a system to equilibrium. It's used in chemical kinetics to indicate that an externally applied influence has shifted the equilibrium position of a reaction, normally abruptly, and that the reaction is adjusting to the equilibrium composition characteristic of the new condition. And this is going to be shown in figure 11.3, which we might as well just jump to now. So in figure 11.3 in the bottom corner, we can see that on the x-axis we have time, and on the y-axis we have concentration, and the relaxation to the new equilibrium composition when a reaction initially at equilibrium at a temperature T is subjected to a sudden change in temperature is what we're looking at. So along the time, we see conditions under T1, which are blue on the x-axis, and then there's an abrupt change in temperature, and you get an exponential relaxation towards the new equilibrium conditions. So going back to the text, we'll consider the response of reaction rates to a temperature jump, in this case, a sudden change in temperature. We know from 7.8 that the equilibrium composition of a reaction depends on the temperature, provided that delta H is non-zero. So a shift in temperature acts as a perturbation on that system. One way of achieving a temperature jump is to discharge a capacitor through a sample made conducting by the addition of ions. But laser or microwave discharges can also be used experimentally. Temperature jumps of between 5 and 10 degrees Kelvin can be achieved in about 1 microsecond with electrical discharge. The high energy output of pulsed lasers is sufficient to generate temperature jumps of between 10 and 30 Kelvin within nanoseconds in aqueous samples, making the technique suitable for the study of the events involved in protein folding. Because if you were to heat things more slowly, the changes would also occur more slowly, and you wouldn't be able to see the instantaneous nature or the rate of how the reaction would chase that temperature change, as compared to having a really fast temperature change that doesn't overdrive the reaction. So equilibria for which there is a change in volume between reactants and products are also sensitive to pressure, and pressure jump techniques may then be used. So it's shown in derivation 11.2 in the text, if you'd like to go through the derivation, that when a sudden temperature increase is applied to a simple A is in equilibrium with product B, or AB equilibrium, that is first order in each direction, the composition relaxes exponentially to the new equilibrium composition with the following relationships, where X, in this case, is the departure from equilibrium at the new temperature, and x0 is the departure from equilibrium immediately after the temperature jump. And we also have a new term, which is tau, which is our relaxation time. So equation 11.4 shows that the concentration of A and B relax into the new equilibrium at a rate determined by the sum of the two new rate constants. Because equilibrium constant under the new conditions is equilibrium constant equals K over K prime, its value may be combined with the relaxation time measurements to find the individual K and K prime. Now, let's take a second from discussing this new topic and let's look a little bit more at the kinetics of protein unfolding. Proteins are polymers that attain well-defined three-dimensional structures both in solution and in biological cells. They're polypeptides formed from different amino acids strung together by peptide linkages. Hydrogen bonds between amino acids of a polypeptide give rise to stable helical and sheet structures, which may collapse into a random coil when certain conditions are changed. For example, the synthetic polypeptide polybenzoglutamate is helical in a non-hydrogen bonding solvent, but in a hydrogen bonding solvent, it forms a random coil. The unwinding or denaturing of a helix into a random coil is a cooperative transition in which the polymer becomes increasingly more susceptible to structural changes once the process has begun. Denaturation can be brought about by changes in temperature or pH, or by reaction with certain compounds such as urea or guanidinium hydrochloride, and these are known as denaturants. Here we examine the kinetics of a helix coil transition, focusing primarily on experimental strategies and some recent results. Earlier work on folding and unfolding of small polypeptides and larger proteins relied primarily on rapid mixing and stop flow techniques. In a typical stop flow experiment, a sample of protein with high concentration of chemical denaturant is mixed with a solution containing a much lower concentration of the same denaturant. Upon entering the mixing chamber, the denaturant is diluted and the protein refolds, although as a caveat, not all proteins can refold following denaturation. Unfolding is observed by mixing a sample of folded protein with a solution containing a high concentration of denaturant. These experiments are ideal for sorting out events on the millisecond timescale, such as the formation of contacts between helical segments of a larger protein. However, the available data also indicate that in a number of proteins, a significant portion of the folding process occurs in less than a millisecond, a time range not accessible by stop flow technique. More recent temperature jump and flash photolysis experiments have uncovered faster events. For example, at room temperature, the formation of a loop between the helical and sheet segments may be as fast as 1 microsecond, and the formation of a tightly packed cores with significant tertiary structure occurs in 10 to 100 microseconds. Among the fastest events are the formation of helices and sheets from fully unfolded peptide chains, and we examine how the laser-induced temperature jump technique has been used in the study of the helix coil transition. The laser-induced temperature jump technique takes advantage of the fact that proteins unfold or melt at high temperatures, and each protein has a characteristic melting temperature. Proteins also lose their native structure at very low temperatures, a process known as cold denaturation, and refold when this temperature is increased but kept significantly below the melting temperature. Hence, a temperature jump experiment can be configured to monitor either folding or unfolding of a polypeptide depending on the initial and final temperature of the sample. The challenge of using melting or cold denaturation as the base of kinetic measurements lies in increasing the temperature of the sample very quickly so fast relaxation processes can be monitored. A number of clever strategies have been employed. In one, a pulsed laser excites dissolved dye molecules that discard the extra energy largely by heat transfer to the solution. Another variation makes use of direct excitation of water, or D2O, with a pulsed infrared laser. The latter strategy leads to temperature jumps in a small irradiated volume of about 20 Kelvin in less than 100 picoseconds. Relaxation of the sample can then be probed by a variety of spectroscopic techniques. Much of the kinetic work of the helix coil transition has been conducted in small synthetic polypeptides rich in alanine, an amino acid that's known to stabilize helical structures. Both experimental and theoretical results suggest that the mechanism of unfolding consists of at least two steps: a very fast step in which amino acids at either end of the helical segment undergo transitions to coiled regions, and a slower, rate-determining step that corresponds to the cooperative melting of the rest of the chain and loss of helical content. Using H and C to denote an amino acid residue belonging to a helical and coiled region, respectively, the mechanism may be summarized as follows, where you have an H, all H to single C transition, which is very fast, and then a all H with one C transitioning to all C, which is the actual rate determining step. The rate determining step is thought to account for the relaxation time of 160 nanoseconds measured with a laser-induced temperature jump between 282.5 Kelvin and 300.6 Kelvin in an alanine-rich polypeptide containing 21 amino acids. It's thought that the limitation of this rate of the helix coil transition in this peptide arises from the activation energy barrier of 1.7 kilojoules per mole associated with initial events of the form, where you have primarily helical and then you go from that to a single substituted coil in the middle of the chain. Therefore, initiation is not only thermodynamically unfavorable, but also kinetically slow. Theoretical models also suggest that transitioning from all helical to a single coil transition at either end of a helical segment has a significantly lower activation energy on account of converting amino acids not being flanked by helical regions. The time constant for the helix coil transition has also been measured in proteins. In apomyoglobin, or myoglobin lacking heme cofactor, the unfolding of the helices appears to have a relaxation time of about 50 nanoseconds, even shorter than in synthetic peptides. It's difficult to interpret these results because we do not yet know how the amino acid sequence or interactions between helices of unfolded proteins affect the helix coil relaxation time. So now that we finished with that light reading, moving back to theory and transitioning to consecutive reactions. It is commonly the case that a reactant produces an intermediate which subsequently decays into a product. Radioactive decay is often of this type, with one nuclide decaying into another, and then that nuclide decaying into a third, like we see here in this example. Note the difference in rate of reaction, where the first step takes 2.35 minutes and the second takes 2.35 days. The times are half-lives given. Biochemical processes are often elaborate versions of this very simple model. For instance, the restrictive enzyme Icari catalyzes the cleavage of DNA and brings about the sequence of reactions where you go from supercoiled DNA to open circle DNA to linear DNA. To illustrate the kinds of considerations involved, we suppose that the reaction takes place in two steps. First, the intermediate one, which is the open circle DNA in this instance, is formed from reactant A, or supercoiled DNA, in a first-order reaction. Then one decays in a first-order reaction to form product P, which in this case is our linear DNA. And we can show this as the following, where reactant A goes to intermediate I, which can be described as a rate of formation of I equals K sub A times the concentration of A. And we can also view it from the perspective of intermediate I going to product P, which can be described by the rate of formation of product P equals K sub B times the concentration of intermediate I. So for simplicity, we're ignoring the reverse reactions right now, which is valid if they're really slow. The first of these rate laws implies that the decay of reactant A is first order, and therefore we can state that the following. And in this case, the net rate of formation of the intermediate is the difference between its rate of formation and its rate of consumption. So we can now write that the net rate of formation of the intermediate is going to be equal to K sub A times the concentration of A minus K sub B times the concentration of I, with concentration of A given by equation 11.5. This equation is more difficult to solve, but is a standard form with the following solution. Finally, because the concentration of A plus the concentration of I plus the concentration of P equals the initial concentration of A at all stages of the reaction, the concentration of P can be stated to be the following. So now we've related the concentration of the product to the initial concentration of our reactant via the following relationships. These solutions are illustrated in figure 11.4, which we see off to the side. We see that the intermediate grows in concentration initially, then decays as A is exhausted. Meanwhile, the concentration of product P rises smoothly to its final value. As we see in derivation 11.3, if you're interested in reading it in the text, the intermediate reaches its maximum concentration at the following time. This is the optimum time for a manufacturer trying to make the intermediate in a batch process to extract it. For instance, if K sub A equals 0.120 units per hour and K sub B is 0.012 per hour, then the intermediate is at a maximum at time equals 21 hours after the start of the process. And now we can move to reaction mechanisms. We've seen how two simple types of reaction, approach to equilibrium and consecutive reactions, result in characteristic dependence of the concentration on the time. We can suspect that other variations with time will act as the signatures of other reaction mechanisms. So, let's start with elementary reactions. Many reactions occur in a series of steps called elementary reactions, each of which involves only one or two molecules. We'll denote an elementary reaction by writing its chemical equation without displaying the physical state of the species, as in hydrogen, not hydrogen gas, but just H, plus bromine gas react to form hydrogen bromide, or plus a bromine. Here. We've already used this convention without comment in some of the reactions discussed in Chapter 10. The equation signifies that a specific hydrogen atom attacks a specific Br2 molecule to produce a molecule of HBr and a bromine atom. Ordinary chemical equations summarize the overall stoichiometry of the reaction and do not imply any specific mechanism. The molecularity of an elementary reaction is the number of molecules coming together to react. In a unimolecular reaction, a single molecule shakes itself apart, or an atom, into a new arrangement, which is what we're seeing in figure 11.5 in the top right. An example of the isomerization of cyclopropane into propane is a great example. The radioactive decay of nuclei, for example, the emission of a beta particle from the nucleus of a tritium atom, which is used in mechanistic studies to follow the course of particular groups of atoms, is unimolecular, in the sense that a single nucleus shakes itself apart. In a bimolecular reaction, two molecules collide and exchange energy, atoms or groups of atoms, or undergo some other kind of change, as in the reaction between H and F2, or between H and Br2, which is what we're looking at in figure 11.6. So in figure 11.5, we're looking at a unimolecular elementary reaction. An energetically excited species decomposes into products. It simply shakes itself apart. Whereas in figure 11.6, we'll see a bimolecular elementary reaction where two species are involved in the process. It's important to distinguish molecularity from order. The order of a reaction is an empirical quantity and is obtained by inspection of the experimentally determined rate law. The molecularity of a reaction refers to an individual elementary reaction that has been postulated as a step in proposed mechanism. Many substitution reactions in organic chemistry, for instance, SN2 nucleophilic substitutions, are bimolecular and involve an activated complex that's formed when two reactive species. And now that I've gotten McAfee to leave my computer screen with a forced update attempt, let's say that again. Many substitution reactions in organic chemistry, such as SN2 nucleophilic substitutions, are bimolecular and involve an activated complex that's formed from two reactant species. Enzyme-catalyzed reactions, which we'll see in 11.13 in just a little bit, can be regarded to a good approximation as bimolecular in the sense that they depend on the encounter of a substrate molecule and an enzyme molecule. We can write down the rate law of an elementary reaction from its chemical equation. First, consider a unimolecular reaction. In a given interval, 10 times as many A molecules decay when there are initially 1,000 A molecules as when there are only 100 A molecules present. Therefore, the rate of decomposition of A is proportional to its concentration, and we can conclude that a unimolecular reaction is first order. The rate of a bimolecular reaction is proportional to the rate at which the reactants meet, which in turn is proportional to both of their concentrations. Therefore, the rate of the reaction is proportional to the product of the two concentrations of an elementary bimolecular reaction, which is second order overall. So here we have our first example, where A proceeds to products and can be described as rate of reaction equals K times the concentration of A exclusively. And here we have our second example where A plus B leads to products, where the rate of reaction equals the rate constant times the concentration of A times the concentration of B. Now that we've worked through these basics, we must now explore how to string simple steps together into a mechanism and how to arrive at the corresponding overall rate law. For the present, we emphasize that if the reaction is an elementary bimolecular process, then it has second-order kinetics. However, if the kinetics are second order, then the reaction could be bimolecular, but might be complex. So, moving on to the formulation of rate laws. Suppose we propose that a particular reaction is the outcome of a sequence of elementary steps. How do we arrive at the rate law implied by that mechanism? We introduce the technique by considering the rate law for the gas phase reoxidation of nitric oxide, nitrogen monoxide, where we have two equivalents of nitrogen monoxide plus oxygen gas yields two equivalents of nitrogen dioxide. Nitric oxide is a very important component of polluted atmospheres. It's formed in the hot exhaust of vehicles and jet engines of aircraft, and its oxidation is a step in the formation of acid rain. The compound is also a neurotransmitter involved in the physiological changes taking place during sexual arousal. Experimentally, the reaction is found to be third order overall, described here, where the rate of reaction equals the rate constant K times the concentration of nitrogen monoxide squared times the concentration of oxygen. One explanation of the observed reaction order might be that the reaction is a single termolecular or 3-molecule elementary step involving the simultaneous collision of 2 nitrogen monoxide molecules and 1 oxygen molecule. However, such collisions occur very infrequently. Therefore, although termolecular collisions may contribute, the rate of reaction by this mechanism is so slow that another mechanism usually dominates. The following mechanism, in this case, has been proposed, where step 1, 2 nitrogen monoxide molecules combine to form a dimer, which is what we're seeing here in A, where we have dinitrogen dioxide. And the rate of formation of this would be described by the rate constant Ka times the concentration of NO squared. This step is plausible because nitrogen monoxide is an odd electron species, a radical, and 2 radicals can pair their electrons and form a covalent bond when they meet. That the N2O2 dimer is also known in the solid makes the suggestion plausible. It's often a good strategy to decide whether a proposed intermediate is the analog of a known compound. So, moving on to step 2, N2O2 dimer decomposes into NO molecules, with the rate of decomposition being equal to K prime A times the concentration of N2O2. This step, the reverse of step 1, is a unimolecular decay. The dimer shakes itself apart. We adopt the convention in which the rate constant of a reverse reaction is marked with the prime, as in K sub A, for the forward reaction K prime A for its reverse. Step 3, alternatively, an oxygen molecule collides with the dimer and results in the formation of nitrogen dioxide, shown here. In this particular case, the rate of consumption of dinitrogen dioxide would equal K sub B times the concentration of N2O2 times the concentration of O2. Now we proceed to derive the rate law on the basis of this proposed mechanism. The rate of formation of product comes directly from step 3. So the rate of formation of nitrogen dioxide would equal 2 times K sub B times the concentration of N2O2 times the concentration of oxygen gas. Which I've redrawn here at the top. So in this case, because everyone's saying where'd the 2 come from, the 2 appears in the rate law because 2 NO2 molecules are formed in each reaction event. So the concentration of NO2 increases at twice the rate that the concentration of N2O2 decays. However, this expression is not an acceptable overall rate law because it's expressed in terms of the concentration of the intermediate N2O2. An acceptable rate law for an overall reaction is expressed solely in terms of the species that appear in the overall reaction. Therefore, we need to find an expression for the concentration of N2O2. To do so, we consider the net rate of formation of the intermediate, the difference between its rate of formation and decay. Because N2O2 is formed in step 1, but decays in step 2 and 3, its net rate of formation can be defined in the following. Note that the formation terms occur with a positive sign and the decay terms with a negative sign because they reduce the net rate of formation. If we could solve this equation for the concentration of N2O2 in terms of the concentrations of NO and O2, we could substitute the result into the preceding expression and obtain the overall rate law. However, this involves solving a very difficult differential equation and will give an enormously complex expression. In fact, even in this relatively simple case, we can obtain only a numeric solution using a computer. To make progress towards obtaining a simple formula, we must make an approximation. And this leads us to our description of the steady state approximation. It's common at this stage of formulating a rate law to introduce our steady state approximation, in which we suppose that the concentration of all intermediates remain constant and small throughout the reaction, except right at the beginning and right at the end. An intermediate is any species that does not appear in the overall reaction but that has been invoked in the mechanism. For our mechanism, the intermediate's N2O2. So we write net rate of formation of N2O2 equals 0, which implies the following. We can now rearrange this equation into an expression for the concentration of N2O2, where N2O2 equals K sub A times the concentration of NO squared over the sum of K sub A prime plus the product of K sub B times the concentration of oxygen. It follows that the rate of formation of NO2 is the following. At this stage, the rate law is more complex than the observed law, but the numerator resembles it. The two expressions become identical if we suppose that the rate of decomposition of the dimer is much greater than the rate of reaction with oxygen. For then, K sub A prime times the concentration of N2O2 would be substantially greater than K sub B times the concentration of N2O2 times the concentration of oxygen, or after canceling this term, when this condition is satisfied, we can approximate the denominator in the overall rate law by K sub A prime alone and conclude the following, that the rate of formation of NO2 is going to equal 2 times the constant K sub A times K sub B over K sub A prime times the concentration of NO squared times the concentration of oxygen gas. This expression has the observed overall third-order form. Moreover, we can identify the observed rate constant as the following combination of rate constants for the elementary reactions. Here. One feature to note is that although each of the rate constants in equation 1111 increases with temperature, that might not be true of K itself. If the rate constant K sub A prime increases more rapidly than the product of Ka Kb increases, then Kr will decrease with increasing temperature, and the reaction will go more slowly as the temperature is raised. The physical reasons is that the dimer N2O2 shakes itself apart so quickly at higher temperatures that its reaction with O2 is less able to take place, and products are formed more slowly. Mathematically, we would say that the composite reaction has a negative activation energy. We have to be very cautious about making predictions about the effect of temperature on reactions that are the outcomes of several steps because of this type of rationale. This takes us to the next section, the rate determining step. The oxidation of nitrogen monoxide introduces another important concept. Suppose that step 3 is very fast, so K sub A prime may be neglected relative to K sub B times the concentration of oxygen in equation 11.9. One way to achieve this condition is to increase the concentration of oxygen in the reaction mixture. Then the rate law simplifies to the following, where the rate of formation of nitrogen dioxide equals 2 times Ka times the concentration of NO squared. Now the reaction is second order in nitrogen monoxide, and the concentration of oxygen gas does not appear in the rate law. The physical explanation is that the rate of reaction of N2O2 is so great on account of high concentration of O2 in the system that N2O2 reacts as soon as it's formed. Therefore, under these conditions, the rate of formation of nitrogen dioxide is determined by the rate at which N2O2 is formed. This step is an example of a rate-determining step, the slowest step in the reaction mechanism which controls the rate of the overall reaction. The rate-determining step is not just the slowest step. It must be slow and be a crucial gateway for the formation of a product. If a faster reaction can also lead to products, then the slowest step is irrelevant because the slow reaction can then be sidestepped, such as in figure 11.7. The rate-determining step is like a slow ferry crossing between two fast highways. The overall rate at which traffic can reach its destination is determined by the rate at which it can make the ferry crossing. If a bridge is built that circumvents the ferry remains the slowest step, but it is no longer rate determining. Let's take a look at figure 11.8. It shows the reaction profile for a mechanism of this kind in which the slowest step is the one with the highest activation energy. So if we take a look at figure 11.8, you can see the reaction profile for a mechanism in which the first step is rate determining, or RDS is our rate determining step. In some cases, reactants can give rise to a variety of products, as in nitrations of monosubstituted benzene, when various proportions of ortho, meta, and pair-substituted products are obtained, depending on the directing power of the original substituents. Suppose two products, P1 and P2, are produced by the following competing reactions, where A plus B can give product 1, and A plus B can give product 2 as well. And they have different rates of formation, where the rate of formation of P1 equals K1 times the concentration of A and B. And the formation of P2 is the rate constant K2 times the concentration of A times the concentration of B. The relative proportions in which the two products have been produced at a given stage of reaction before it's reached equilibrium is given by the ratio of the two rates, and therefore to the two rate constants, which is what we see here, where the ratio of product 2 over product 1 is equal to the rate constant of 2 over the rate constant of 1. This ratio represents the kinetic control over the proportion of products and is a common feature of the reactions encountered in organic chemistry, where reactants are chosen that facilitate pathways favoring the formation of desired products. If a reaction is allowed to reach equilibrium, then the proportion of products is determined by thermodynamic rather than kinetic considerations, and the ratio of concentrations is controlled by consideration of the standard Gibbs energies of all the reactants and products. But if we don't let it reach equilibrium, the faster one's going to predominate, and that gives us the opportunity to pick which one's favored, even in a case where perhaps we have a faster reaction which is not favored at equilibrium. And the last topic for this sub-lecture, before we take a break and then record the second half of the chapter, is unimolecular reactions. Oh, actually, let me check something really fast. Okay, good. That's actually a good place to call it. So unimolecular reactions. A number of gas phase reactions follow first-order kinetics, as in the isomerization of cyclopropane mentioned earlier, in which the strained triangular molecules burst open into an acyclic alkene. In this particular case, the cyclopropane is our reactant, and it opens to the following product, this acyclic alkene. And the rate of this reaction can be described simply as V equals K times the concentration of the reactant cyclopropane. The problem with this reactions like this is that the reactant molecule presumably acquires the energy it needs to react by collision with other molecules. Collisions, though, are simply bimolecular events, so how can they result in a first-order rate law? First-order gas phase reactions are widely called unimolecular reactions because, as we'll see, the rate-determining step is an elementary unimolecular reaction in which the reactant molecule changes into the product. This term must be used with caution, however, because the composite mechanism has bimolecular as well as unimolecular steps. The first successful explanation of unimolecular reactions is ascribed to Friedrich Lindemann in 1921, and the Lindemann mechanism is as follows. Step 1. A reactant molecule A becomes energetically excited by collisions with another A molecule. So A plus A leads to one of them being excited, and the rate of formation of the excited A equals the rate constant K sub A times the concentration of A squared because it has two equivalents of A interacting. Step 2, the energized molecule might lose its excess energy by colliding with another molecule, in which the excited form of A collides with another non-excited A, and they both become not excited. That means we could describe the deactivation of A with the K sub A prime times the concentration of excited A times the concentration of non-excited A. In step 3, alternatively, the excited molecule might shake itself apart and form product P. That is, it might undergo the unimolecular decay. And in this case, excited A will transition to P, where the formation of P is K equal to K sub B times the concentration of excited A, or the rate of consumption of excited A equals K sub B times the concentration of excited A. Now, if the unimolecular step, step 3, is slow enough to be the rate-determining step, then the overall reaction will have first-order kinetics, as we observed, because the rate of reaction will be determined by a first-order kinetic. We can demonstrate this conclusion explicitly by applying the steady-state approximation to the net rate of formation for the intermediate excited A and find that the rate of formation of product P equals K times the concentration of A, where K sub R equals K sub A times K sub B over K sub A prime. This rate law is first order, which is what we were setting out to show. This is a really good place to take a break, and we're going to pick it up next with reactions in solution. So I'm going to upload this video for everyone, and then we'll pick it back up with reactions and solutions next.